Right now, you weigh something, step on a scale and it shows a number, but almost none of that weight comes from where you would guess. Most people say one thing gives you your mass, the Higgs field. Scientists spent 50 years hunting for its particle. They finally caught it in 2012. Then came the twist. The Higgs explains only about 1% of what you weigh. So where does the other 99% hide? The answer is packed inside every atom in your body. A storm of pure energy, racing near the speed of a light chained together by the strongest force in nature. We will crack open a proton. We will switch off the forces holding you together. We will watch your mass get born seconds after the Big Bang. If wonder like this keeps you up at night, like and subscribe. Prepare yourselves. We begin. Every morning somewhere, a person steps onto a small scale on a cold tile floor. A number blinks up. Maybe it says 140 pounds, maybe 200. Whatever shows, that person believes they just learned how much stuff they are built from. They learned the wrong thing. That scale measures one job only. It measures how hard the earth pulls you down. Press your feet on the floor, and gravity drags your whole body toward the center of the planet. The scale feels that pull and turns it into a number. That number is your weight. Your weight can change while every single piece of you stays exactly the same. Fly to the moon, and the very same body reads about 1/6 of those pounds. The moon tugs softer, so the scale relaxes. Float in deep space, far from any planet, and the scale would drop to 0. You would still have your arms, your bones, your beating brain. You would simply weigh nothing. So weight is a trick of location. Move somewhere new and the number moves with you. Under that weight hides the real thing. Scientists call it mass. Mass is the amount of you that stays true no matter where you float. On Earth, on the moon, in the black gap between stars, your mass holds steady. It is the honest measure of how much you are. Here comes the strange part. Almost nobody can tell you where that mass comes from. Ask a science teacher and you get one quick answer. A field. An invisible something spread through all of space, handing weight to everything it touches. It sounds clean. It sounds finished. Case closed. That answer is a trap. The invisible field is real. It won a group of scientists the highest prize in all of physics. It took the largest machine humans have ever built to prove the thing exists. Yet when you finally add up its work, it explains barely a sliver of you. Picture your whole body as 100 coins stacked on that scale. The famous answer, the one every textbook repeats, pays for exactly one of those coins. One single coin, the other 99 coins come from somewhere else, somewhere hidden, somewhere far stranger than a quiet field soaking through empty space. Those 99 coins are pure energy, raw energy, trapped and screaming inside every speck of your body, moving so fast it nearly touches the speed limit of the universe. You're barely built from matter at all. You're mostly trapped motion, frozen into the shape of a person and told to stand still. To see it, we have to shrink down, way down, past your skin, past your cells, past the atoms that build them. We have to crack open the tiniest bricks inside you and stare hard at what glues them together. And what glues them together is the most violent force in all of nature, a force so strong you have never once felt it, because it never loosens its grip long enough for you to notice. Before we weigh you honestly, one thing needs settling first. We need to know what mass truly is, the thing under the number, the thing the floor could never show you, because mass is about how fiercely the universe fights you when you try to move. And that idea alone is stranger than any scale could ever show. 2 shopping carts sit side by side in a parking lot. One is empty. One is packed with heavy bags of dog food. Give each a hard shove with the same push. The empty cart shoots forward. The full cart barely rolls. You just met mass, the real kind. Mass is how hard a thing fights back when you try to move it. Push it, and it pushes against you. The more mass it holds, the harder it digs in its heels. Scientists have a word for this stubbornness. They call it inertia. A thing wants to keep doing whatever it is already doing. Sitting still, it wants to stay still. Moving, It wants to keep moving. People mix this up with weight all the time. They feel a heavy bag pull down on their arm and think that pull is the whole story. The pull is only gravity. Mass is the deeper thing hiding under it. Here is how to catch the difference. Imagine you float inside a space station way up above the Earth. Everything drifts. A bowling ball hangs in the air in front of you, weighing nothing at all. Now try to swat it across the room. Your hand slams into it and stops cold. The ball barely budges and your fingers sting. That ball has no weight up there. It still has all its mass. The stubbornness stayed even when the pull vanished. So mass shows up in two ways. It decides how strongly gravity grabs you, and it decides how hard you are to push around. Same number, two faces. Now shrink the idea down to the smallest things that exist. Every atom in your body is built from tiny pieces. Each of those pieces has its own little mass. Each one fights back when a force tries to move it. Stack up enough of those tiny fights and you get the full stubbornness of your whole body. Which raises a simple question that sounds almost childish. Where does that stubbornness come from in the first place? Why does one tiny piece dig in its heels while another slides through the world like it weighs nothing? Think about light for a second. Light is made of tiny packets called photons. A photon has zero mass, nothing to push against, so light flies at the fastest speed the universe allows, and nothing can slow it down or speed it up. It never fights back, because there is nothing there to fight. Other tiny pieces are the opposite. They drag, they resist. They feel heavy for their size. Something is grabbing them, holding them, making them hard to shove. For 50 years, the smartest people alive stared at this puzzle and had no clean answer. Why do some pieces of the world carry this stubbornness while others carry none? What reaches into the smallest bricks of everything and hands them their mass? Then a shy scientist, working with pen and paper, dreamed up an answer so bold it sounded like magic. He imagined an invisible ocean hiding inside empty space, a thing you could never see, never touch, never drain away, a thing that fills every inch of the room you're sitting in right now. And every particle that carries mass, he said, gets it by wading through that ocean. The world laughed at first, then the world spent half a century and billions of dollars trying to prove him right. In 1964, a quiet man in Scotland went for a walk in the hills and came back with an idea that would take 50 years to test. His name was Peter Higgs. He was a physicist, the kind of scientist who chases the smallest pieces of the world, and he was stuck on the same puzzle that stumped everyone. Why do the tiny bricks of matter have mass at all? The rules of physics back then had a crack in them. On paper, the math worked beautifully only if every particle raced around at light speed weighing nothing. Clean, simple, also completely wrong, because you exist. Your body has mass. The chair under you has mass. Something in the real world was handing weight to particles that the equations wanted to leave weightless. Higgs found a way to fix the crack. He imagined a field. A field sounds fancy, so picture something you already know. Temperature is a field. Every point in your room has a temperature, a number sitting there in the air whether you measure it or not. A field is just a thing that has some value at every single spot in space. It is everywhere at once. Higgs dreamed up a brand new field, one nobody had ever seen. It filled the whole universe. It soaked into every gap, every corner, every empty inch. There was no place you could go to escape it. It was in the room with him. It is in the room with you. And this field did one special job. It grabbed at certain particles as they moved through it. It slowed them down. It made them harder to push. It gave them stubbornness. It gave them mass. The idea was gorgeous. It plugged the hole in the math perfectly. Suddenly the equations worked, and particles could carry weight while still obeying the rules. One problem. Nobody could prove the field was real. You cannot scoop up a jar of it. You cannot shine a light on it. It hides inside empty space, silent and invisible, doing its work where no eye can reach. For all anyone knew, Peter Higgs had written the most beautiful guess in history and nothing more. Years passed, then more years. The idea sat in textbooks with a giant question mark hanging over it. Some scientists believed, some rolled their eyes. A few started calling the mystery particle a nickname that made Higgs cringe. They called it the God particle, as if finding it would explain the whole of creation. Slowly, one truth took hold across the world of science. If this field was real, it should leave a fingerprint. Poke the field hard enough, in just the right way, and a tiny piece of it should pop out for a flash of a second. A particle. Proof you could actually detect. To poke it, though, you would need more energy than any machine on Earth could make. You would need to smash things together harder than they had ever been smashed. You would need to build something monstrous, so they built it. Under the border of 2 countries, in a tunnel longer than most cities, engineers dug a ring and filled it with the coldest, fastest, most powerful machine our species has ever made. They aimed it straight at Peter Higgs's ghost, and what they caught changed how you should see your own body forever. Picture the whole universe filled to the brim with an invisible ocean. It is thinner than water and far stranger, with no colour and no weight of its own. It has no waves you can surf and no shore you can stand on. It simply exists everywhere, all the time. This is the Higgs field, and you're soaking in it right now. It passes through your walls, your skin, your bones, without you feeling a thing. Every particle in your body swims through this ocean every second of your life. Some swim easily, some barely move. That difference is where mass is born. Here is a way to feel it. Imagine walking across an empty gym floor. Nothing in your way. You stride fast, easy, free. Now flood that same gym waist deep with thick syrup. Try to walk again. Every step is a battle. The syrup drags on your legs and slows you down. You feel heavy, even though your body has not changed at all. The stuff around you is doing it. The Higgs field works like that syrup, but only for certain particles. Some particles it grips tight, dragging on them, making them hard to move. Those particles come out heavy. Other particles slip through the same ocean like it is barely there. Those come out light or weigh nothing at all. Scientists have a second picture that helps even more. Imagine a famous pop star walking into a crowded party. The second she steps in, fans swarm her. They cluster around, slowing her every step, making it hard for her to cross the room. She moves like she suddenly weighs a ton. Now picture a random stranger walking into the same party. Nobody notices him. He strolls straight across the room, quick and light. No crowd in his way. The crowd is the Higgs field. The pop star is a heavy particle, mobbed and slowed. The stranger is a light particle, ignored and free. Same room, same ocean, wildly different weight, all from how much attention each one draws. So the field plays favourites. That is the secret sauce. If it dragged on everything equally or nothing at all, our universe would fall apart. Some particles have to be heavy to build solid matter. Some have to stay light or weightless to carry light and hold atoms together. The Higgs field sorts them, handing out weight in different sizes to different players. This raises a question that should bug you. What decides how much the crowd swarms each particle? Why does the field mob one and ignore another? 2 particles can sit in the very same ocean, and one comes out heavy while its neighbour comes out feather-light. The answer lives in how strongly each particle talks to the field. Some are born to grab on hard, some are born to barely touch it. That built-in habit decides their entire weight. And once you understand that, a shocking door swings open. Because it means mass is a relationship, a conversation between a particle and the ocean it swims in. Change the conversation, and you change the weight. For a long time, this was pure theory, beautiful math on a page. To trust it, scientists needed to reach into the ocean and yank out a single drop, a lone piece of the field itself, and hold it up as proof. In the summer of 2012, deep underground, thousands of them held their breath and watched a screen. Turn on a flashlight and something impossible happens instantly. The light leaps out and crosses the room before you can blink. It hits the fastest speed anything in the universe is allowed to reach. Nothing can catch it. Nothing can outrun it. And it can do this for one strange reason. Light weighs nothing at all. Light is made of tiny packets called photons. A photon never talks to the Higgs field. It swims through that invisible ocean like the ocean is barely there. No drag, no grip, no slowing down. So a photon carries zero mass, and a thing with zero mass has no choice but to fly at full speed forever. That is one end of the scale. Total freedom. total lightness. Now swing to the other end, and the numbers get wild. Deep inside your atoms live particles called quarks. Most quarks are fairly light, but there is one monster quark called the top quark that grabs the Higgs field harder than anything else known to science. It drags through that ocean like a truck stuck in mud. How heavy does that make it? A single top quark weighs about as much as an entire atom of gold. One tiny piece, as heavy as a whole atom made of many pieces. It is the heaviest particle we have ever found. Between the flying photon and the monster top quark sits everything else. Each particle grabs the field by its own amount. Grab hard, come out heavy, barely touch, come out light, touch nothing, weigh nothing, and fly like light. Think of the Higgs field as a toll booth stretched across the whole universe. Every particle in creation has to drive through it. The photon zips past and pays nothing, so it stays weightless and fast. A light quark slows for a moment and pays a small toll, coming out with a little mass. The top quark practically crashes into the barrier and pays an enormous fee, coming out heavier than anything else alive. The size of the toll each one pays becomes its mass. Same booth, wildly different bills. Now here is where your gut starts to lie to you. You might think, fine, the Higgs field builds mass, so the Higgs field must build me. I am made of particles. Particles get mass from the field. Add it all up and the field explains my whole body. That feels airtight. It is also the exact place where nearly everyone goes wrong. Because the particles that carry most of your weight barely lean on the Higgs field at all. The heavy hitters inside your body draw almost nothing from that ocean. Their real weight comes from something the Higgs story never mentions. But nobody could say that with certainty until the field itself stopped being a guess. For 50 years it lived only in equations, a brilliant maybe, a ghost that refused to show its face. To turn the maybe into a yes, scientists needed to catch the field in the act. They needed to strike empty space so hard that a chip of the Higgs field would break loose and flash into view, just long enough for a machine to see it. That meant building the biggest, coldest, most powerful machine in human history and running it at full blast over and over, waiting for one impossible flicker. In 2012, after decades of hunting, the flicker finally came. And the moment it did, everything the world believed about its own weight was about to be quietly turned upside down. Under the green fields on the border between France and Switzerland runs a tunnel shaped like a giant ring. It is huge. The ring stretches about 17 miles around, longer than a marathon runner covers in a race. It sits deep underground, hidden below farms and villages where people live their normal lives, never guessing what roars beneath their feet. This machine is called the Large Hadron Collider. It is the biggest machine humans have ever built, and it was made to do one violent thing: smash tiny pieces of matter together as hard as physically possible. Here is how it works. Scientists take tiny particles smaller than atoms and send them racing around the ring. Powerful magnets whip them faster and faster until they scream around the loop nearly at the speed of light. Then, at chosen points, two streams flying in opposite directions crash head-on. The magnets that steer them must be colder than deep space itself. Parts of this machine sit at a temperature colder than the darkest, emptiest corner of the universe. Right next door, when the particles crash, the tiny explosions burn hotter than the center of the sun. The hottest and coldest spots in the whole solar system sitting a few feet apart inside one machine. Why smash things at all? Because when particles crash that hard, their energy turns into brand new particles that burst out of the wreck. For the tiniest sliver of a second, things appear that never show up in our calm, cool world. Detectors the size of buildings watch every crash, snapping pictures billions of times a second, hunting for something rare. The scientists were hunting for one thing above all: the fingerprint of the Higgs field. If Peter Higgs was right, then smashing hard enough should knock a single piece of the field loose. That piece is called the Higgs boson. Find it, and you prove the invisible ocean is real. Miss it, and 50 years of theory might collapse. They crashed particles for months, billions of collisions, mountains of data, teams of thousands sifting through the wreckage, looking for a pattern hiding in the noise. Then, on the 4th of July 2012, they called a meeting. The room was packed. Peter Higgs himself sat in the audience. Old now, grey-haired, decades removed from that walk in the Scottish hills. Scientists had camped outside the doors overnight just to get a seat. The screens flicked on, the data came up. There it was, a bump in the graph, a signal, clean and clear, sitting exactly where the Higgs boson should be. They had caught the ghost. The field was real. The room exploded. People cheered and cried. Peter Higgs wiped tears from his eyes, watching a lifetime of doubt turn into proof. The next year, he won the Nobel Prize, the highest honour in all of science. Newspapers around the world ran the same headline: "Scientists find the particle that gives everything its mass. The mystery of mass solved at last. Case closed." That headline felt like a finish line. It was hiding a secret in plain sight. Because the Higgs boson they caught, the field they finally proved, does one small job in your body, a real job, a tiny one. It explains almost none of what you weigh, and the people cheering in that room already knew it. The scientists who found the Higgs boson kept a strange fact quiet during the cheering. The field they had chased for 50 years, the field the whole world was celebrating, pays for only about 1% of your weight. 1%. Out of your entire body, the famous Higgs field explains a sliver so thin you would round it away by accident. That one number flips the whole story. Every headline said the Higgs gives everything its mass. The truth is much smaller and much stranger. The Higgs gives a tiny fraction of your mass. The other 99 parts come from a source most people have never even heard of. Picture your body weight as a full dollar, 100 cents. The Higgs field drops a single penny into the jar. That penny is real. It matters. Take it away, and some things would break. But it is 1 penny out of 100. Where are the other 99 cents coming from? To find them, you have to go inside, down past your body into your atoms. Everything you are is built from atoms. Trillions upon trillions of them, far too many to count, packed into every cell. Each atom is mostly empty space, with a tiny heavy clump sitting right in the middle. That clump is called the nucleus. It is the heart of the atom, and it holds nearly all the atom's weight. Here is the thing worth staring at. Almost your entire mass lives in those tiny nuclear clumps. Your skin, your blood, your brain, all of it gets its heft from these specks buried deep inside every atom you own. If you could strip away everything but the nuclei of your body, the leftover clump would weigh nearly as much as you do now. It would just fit into a space smaller than a grain of dust, so your weight lives in the nucleus, and the nucleus is built from smaller pieces still, little balls called protons and neutrons, jammed together in a tight knot. These are the heavy hitters, the real giants of your body. Protons and neutrons carry the 99 cents the Higgs field never touched. Whatever gives them their mass gives you almost all of yours. Now you can ask the sharp question: where do protons and neutrons get their weight? If the Higgs field only pays a penny, what pays for the rest? The easy guess is that they are just heavy on their own, solid little balls of stuff, dense and full like tiny marbles. That guess feels right. That guess is completely false. Because a proton is mostly roaring emptiness. Crack one open, and you find almost nothing inside but a few tiny specks, floating in a storm with vast gaps between them. The specks themselves weigh next to nothing. Add up the actual stuff inside a proton, the real solid pieces, and it comes to a shockingly small amount. Nowhere near enough to explain the proton's full weight, so the proton weighs far more than the things it is made of. That should be impossible. A box cannot weigh more than everything you put in it. Yet the proton does exactly that. And figuring out how is where this story stops being simple and starts being unbelievable. We need to crack a proton open and count what falls out. Hold up your hand and look at it. It feels solid. It looks full. You could knock it on a table and hear a firm thud. Every instinct tells you your hand is packed with stuff, wall to wall. Your hand is almost entirely empty space. Zoom into a single atom in your fingertip. If you blew that atom up to the size of a giant sports stadium, the whole thing would be empty air, except for one tiny marble sitting dead center on the 50-yard line. That marble is the nucleus. Everything else, the entire stadium of space, is basically nothing. A faint blur of electrons whizzing around the far edges, and a vast void between. That marble at the center holds nearly all the weight of the atom. The heavy giants live there. Protons and neutrons crammed together into a knot so tiny it makes the rest of the atom look like an ocean of emptiness. How many of these giants are inside you? The number is too big for your brain to picture. Your body holds so many protons and neutrons that if you tried to count them one per second, you would need far longer than the entire age of the universe, many times over. They fill every atom in every cell in every inch of you, an uncountable army of tiny giants, and together they carry almost your whole weight. Now here is the fact that should make your head spin. These giants are packed unbelievably tight, so tight that the empty space in atoms is the only reason you're not impossibly heavy. Imagine you could squeeze all the empty space out of your atoms, crush every stadium down until the marbles touched, pack the nuclei shoulder to shoulder with no gaps at all. Your entire body would shrink to something smaller than a speck of dust, and that speck would still weigh what you weigh right now. Every pound of you folded into a dot you could lose in the carpet. Push that even further. A single sugar cube of this pure nuclear matter packed with no empty space would weigh about as much as a mountain. One tiny cube, heavier than a peak you could see from miles away. That is how dense the giants really are, and how much emptiness normally hides between them. So your solid, firm, thuddable hand is mostly a beautiful illusion. A wide net of empty space, held open by a scattering of dense, heavy specks. You're far more nothing than something. And those dense specks, the protons and neutrons, hold the answer to the whole mystery. They carry the 99%. Crack their secret, and you crack the secret of your own weight. So it is time to do the impossible. It is time to pick one single proton, one lonely giant out of the uncountable army, and pry it open to see what sits inside. Everyone expects the same thing. A tiny solid ball. Dense, full, packed with weight. Something that clearly deserves to be as heavy as it is. That expectation is about to shatter, because when scientists finally looked inside a proton, they found something that made no sense. A near-empty room, a few faint specks that weigh almost nothing, and a violent storm of pure force screaming in the gaps. The specks could never explain the weight. So what does? To look inside a proton, you cannot use a knife. It is far too small for any blade. So scientists did something cleverer. They took tiny bullets, even smaller than the proton, and fired them straight at it, over and over, harder and harder. Then they watched how the bullets bounced. From the way things ricocheted, they could map what was hiding inside the same way you might figure out the shape of a dark room by throwing marbles in and listening to the bounces. For a long time, they thought the proton might be one smooth, solid lump. If so, the bullets should skim off gently, like a stone skipping on a pond. The bullets did something else entirely. Sometimes they slammed into something small and hard deep inside the proton and bounced back violently, like they had hit a tiny rock buried in soft sand. The proton was rough and lumpy inside. It held real, solid, separate pieces. Those pieces got a name. Quarks. A proton, it turned out, is built from 3 of these quarks. 3 tiny specks, floating inside that near-empty room, making up the core of the proton. Neutrons are the same story, 3 quarks each, in a slightly different mix. Every proton and neutron in your body, every one of those uncountable giants, is really a little bag holding 3 quarks. Quarks are strange in ways that break your everyday sense of the world. You can never pull one out on its own. Never. No matter how hard scientists smash and pry, a single quark refuses to come out alone. They only ever appear locked together in groups hidden inside protons and neutrons, and they fight with everything they have to stay that way. So now the picture sharpens. Your weight lives in your atoms. Most of that weight lives in the nuclei. The nuclei are built from protons and neutrons are built from 3 quarks each. Follow the trail all the way down, and you land on quarks. Which means the answer should be simple now. If protons are heavy, and protons are made of 3 quarks, then the quarks must be heavy too. Weigh the 3 quarks, add them up, and you should get the full weight of the proton. Case closed, mystery solved. So scientists weighed the quarks, and the number they got broke everything. The 3 quarks inside a proton, added all together, weigh almost nothing. A tiny scrap. A whisper. They come to only about 1% of the proton's total weight, or even less. Read that again slowly. The proton is built from 3 quarks. The 3 quarks weigh 1% of the proton. So what makes up the other 99% of the proton's weight? There is nothing else in there. No fourth quark hiding in the corner, no secret heavy ball, just 3 feather-light specks and a whole lot of seemingly empty space. A box holding 3 feathers should weigh about as much as 3 feathers. This box weighs 100 times more than the feathers inside it. Something in that near-empty space is carrying almost all the weight. Something you cannot see, cannot touch, and have never once felt. To find it, we have to weigh a quark for ourselves and stare at just how absurdly light it really is. Put a single quark on the most sensitive scale imaginable, and the needle barely twitches. The quarks that build your protons come in 2 main kinds, called up quarks and down quarks. Both are absurdly light. To picture how light, shrink everything down together. If a proton weighed as much as a full school bus, the 3 quarks inside it would together weigh less than a couple of apples tossed on the back seat. The bus is heavy. The apples are almost nothing, yet the apples are supposedly what the bus is made of. Where does even that tiny quark weight come from? Here is the twist that ties back to the start of our story. That little scrap of quark mass is the Higgs field at work. When the Higgs field grabs a quark and drags on it through the invisible ocean, it hands the quark its small weight. The quark's mass is the toll it pays swimming through the field. So the famous Higgs penny, the 1% of you everybody celebrated, is mostly this. It is the tiny weight of your quarks. That is the real job the Higgs field does inside your body. It gives your quarks their whisper of mass, and stops there. The Higgs field is doing exactly what Peter Higgs promised. It is real. It is working. It is handing out mass. It just turns out that the mass it hands out is a rounding error compared to the whole. Now the mystery stands out sharp and clear. Your quarks are light. The Higgs field that weighs them is only good for 1%. But the proton, the bag holding those 3 light quarks, is 100 times heavier than its contents. Think about what that really means. You could gather every solid particle inside a proton, every quark, weigh them all with a perfect scale, and you would come up with almost nothing. The proton, though, is heavy. Heavy enough to build a mountain, a planet, a person. Heavy enough to be you. The weight is real. The stuff carrying it seems to be missing. This should feel wrong in your bones. In your whole life, a full box always weighs about as much as the things inside it. Fill a backpack with books, and the backpack weighs the books. Nowhere on Earth does an empty-looking bag weigh 100 times more than the tiny scraps floating in it. Yet that is exactly what a proton is. A near-empty bag that weighs 100 times more than its own contents. Every proton and neutron in your body pulls off this same impossible trick over and over, trillions of times, and the total is the number you read on your bathroom scale. So the weight comes from somewhere the ordinary scale of stuff cannot reach. It comes from the space between the 3 specks, from something living in the gaps. There is only one thing left in there, a force, the thing that holds the quarks together and refuses to let them escape. The strongest, most violent force in the whole of nature. And that force, it turns out, has a weight of its own, a weight that becomes your weight. To understand how a force can weigh anything at all, we have to meet the strongest of them, the one you have never felt, the bully that runs the tiny world inside you. Step back and look at what the evidence is telling us. Your weight lives in your protons and neutrons. Those are built from 3 tiny quarks each. The quarks weigh almost nothing. The Higgs field that weighs them covers only a penny of the dollar. Add up every solid thing inside you, every real particle, and it falls 100-fold short of what you actually weigh. The stuff cannot explain you. So the answer must be something beyond ordinary stuff. Detectives call this the process of elimination. Cross off every suspect that could not have done it, and whatever remains, however impossible it seems, has to be the truth. We have crossed off the quarks. We have crossed off the Higgs field. Only one suspect is left standing in that near-empty proton. The suspect is energy. Raw, pure energy, packed into the space inside every proton and neutron in your body. And this is the idea that changes how you should see yourself forever. Energy has weight. When you trap energy in a tiny space and hold it there, it starts to act exactly like mass. It resists being pushed, it bends gravity, it tips a scale. So the 99% of you that the Higgs field cannot explain is trapped energy, wearing the costume of solid matter. Sit with what that means about your own body. You feel solid. You bump into doors. You lift heavy bags. Every ounce of that feeling of being a physical thing is mostly an illusion built out of caged energy. If you could weigh only the true material inside you, the actual particles, you would be almost weightless. The rest, the vast bulk of you, is energy the universe locked up long ago and never released. You are less a pile of bricks and more a bonfire that someone froze in place. The flames are still roaring inside every proton. You just cannot see them from out here. This should sound impossible, and for a while it puzzled the greatest minds alive. How can nothing weigh something? How can pure energy, with no solid form, press down on a scale? A flame slips away the moment you grab at it. A beam of light passes right through your fingers. How does energy turn into the very heft of your bones? The answer runs through two of the deepest ideas in all of science. One is a force, the strongest force there is, the one doing the trapping. The other is a single short equation, the most famous line ever written in physics, that reveals energy and mass to be two faces of the same coin. Meet the force first. It is called the strong force, and it is the reason you exist as a solid being at all. It is 100 times mightier than the force that shocks you when you touch a doorknob. It is the glue holding every proton and neutron together against pressures that should rip them apart in an instant. Yet you have lived your whole life and never felt it once. Never. It hides so well that for most of human history nobody knew it was there. To see how a force this violent can stay completely invisible, and how it manages to weigh as much as a whole human being, we have to shrink down one more time and step inside its cage. There are only 4 forces in the entire universe. Every push, every pull, everything that ever happens comes from just these 4. You already know 2 of them well. Gravity is one. It pulls you to the ground and holds the moon near the Earth. It feels powerful because it never lets you float away. Yet gravity is secretly the weakest force of all, by a laughable amount. A tiny magnet, small enough to hold in your fingers, can lift a paperclip straight off the floor. That little magnet just beat the entire pull of the whole planet. That is how weak gravity really is. The second force you know is the one in that magnet, and in every wire and spark and screen you own. It handles light, electricity, and the way atoms stick together to build everything you touch. It is far stronger than gravity. It runs your whole daily world. The other 2 forces hide inside the atom, where you can never see them, and one of them is the reason you have any weight at all. They call it the strong force. The name is honest. It is the strongest force in all of nature, the undefeated champion. Line the 4 forces up in order of muscle, and the strong force sits at the very top, towering over the rest. It is more than 100 times mightier than the force that runs electricity. Nothing else even comes close. So here is the question that should stop you cold. If the strong force is the most powerful thing in the universe, why have you never felt it? Not once in your entire life. You feel gravity every second. You feel static shocks and magnets. Yet the strongest force of all has stayed completely hidden. The answer is its reach. The strong force is a monster with the arms of an ant. Gravity reaches across the entire universe. It ties galaxies together over distances so vast that light takes billions of years to cross them. The strong force is the opposite kind of giant. It is unbelievably powerful, but only across a distance smaller than a single proton. Step even a hair outside that range, and the strong force simply vanishes, as if it were never there. Picture the strongest man on Earth, able to lift a car over his head. Now shrink his arms until they are shorter than an eyelash. He's still incredibly strong. He just cannot reach anything outside his tiny bubble. That is the strong force, all its power locked inside a space too small to touch your world. So it works in secret. Deep inside every proton and neutron in your body, this force is roaring at full blast right now, gripping the quarks with unimaginable strength. It never rests. It never weakens inside its range. It holds the giants of your body together with a grip nothing can break. And here is the payoff you have been chasing. That grip, that violent effort to hold the quarks, costs a staggering amount of energy. And by the deepest rule in physics, that trapped energy shows up as weight. Your weight. The strong force carries your mass by working so hard in such a tiny space that its effort turns into heft. But a force needs something to carry it. Gravity has its pull, electricity has its spark. What carries the strongest force of all? What actually reaches out and grips the quarks? The answer is a particle so strange it is built from nothing but energy. The strong force needs a messenger, a tiny thing that flies between the quarks and carries its grip. That messenger has a fitting name. Scientists call it the gluon because it works like glue, sticking the quarks together inside every proton and neutron. Gluons zip back and forth between the quarks constantly, billions upon billions of times, weaving an unbreakable web that holds the whole thing shut. Here is the first shock about gluons. A gluon weighs nothing. Zero mass, just like a particle of light. On its own, a single gluon is weightless, a pure flash of force with no heft at all. So now the mystery gets even sharper. Your weight comes from inside the proton. Inside the proton, the quarks are almost weightless, and the gluons, the glue, filling the space between them, are completely weightless. Every single ingredient inside a proton weighs next to nothing, yet the proton is heavy. How can a bag of weightless glue and near-weightless specks weigh as much as it does? The secret is what the gluons are doing. A gluon may weigh nothing sitting still, but gluons never sit still. They swarm through the proton in a frenzy, carrying the full fury of the strongest force in nature. That endless, violent activity is packed with energy, colossal amounts of it, crammed into a space smaller than you can imagine. Think of it like this. A single spark is tiny and harmless, but fill a room with a raging fire, and the room holds an enormous amount of energy, even though fire itself is something you cannot pick up and weigh. The gluons inside a proton are like a fire that never goes out, roaring in a space 1 trillion times smaller than a grain of sand. The energy of that fire is immense, and energy, when you trap it, becomes weight. That is the rule the whole universe runs on, and it is coming next. The gluon field inside a proton is the true heavyweight. It carries far more of your mass than the quarks and the Higgs field combined. When you step on a scale, most of that number is really the energy of gluons flying between quarks at blinding speed, glued to their work forever. Sit with how strange this is. You have always thought of yourself as made of things, solid, weighable things, like tiny marbles stacked into a body. The truth is wilder. Most of you is made of activity, motion, the furious flinging of weightless glue between weightless specks. Freeze all that motion, and most of your weight would simply disappear. You are, in large part, a process that refuses to stop. A storm the universe started long ago and never calmed. The roar of that storm is what you weigh. There is one piece missing to make this make full sense. We keep saying that energy becomes weight, that trapped motion becomes mass. That sounds like a magic trick or a cheat. How can something with no solid form, no substance you can hold, press down on a scale and tip it? For that, we need the single most famous idea in the history of science. A short line, scribbled by a young clerk in a patent office, that revealed a secret hiding in plain sight for all of time. Energy and mass, that line says, are the same thing wearing two different masks, and once you truly understand it, your own body will never look the same again. In 1905, a young man sat at a desk in a patent office, bored, daydreaming about light. His name was Albert Einstein. Almost nobody knew his name yet. He spent his days stamping papers for other people's inventions. But in his spare moments, he was quietly rewriting the rules of the universe. And that year, he scribbled down an equation so simple a child can memorize it, and so deep that scientists are still unwrapping it today. Energy equals mass times the speed of light, times the speed of light again. Strip away the math, and here is what it really says. Energy and mass are the same thing. You can turn one into the other. Mass is really a huge amount of energy, frozen into solid form, and energy, if you pack enough of it into one place, becomes mass. The speed of light in that equation is a gigantic number. Multiply by it twice, and even a tiny scrap of mass hides an unbelievable amount of energy. That is why a nuclear bomb using a lump of material smaller than your fist can level a whole city. All that destruction was energy, sleeping inside a small piece of matter, suddenly set free. Now flip the equation around, and you find the answer to our whole mystery. If mass can turn into energy, then energy can turn into mass. Trap a bunch of energy in a small space, hold it there, and it starts to weigh something. It resists being pushed exactly like matter does. It bends gravity exactly like matter does. A scale cannot tell the difference. To the scale, trapped energy simply is mass. This is the missing key. Inside every proton, the strong force and its gluons are storing a staggering amount of energy in an incredibly tiny space. By Einstein's rule, that trapped energy must show up as weight. And it does. It shows up as almost all of the proton's mass, which is almost all of your mass. So when you step on a scale, most of the number you see is Einstein's equation, running inside you trillions of times over. It is energy, locked into the shape of matter, being counted as weight. This should reshape how you see yourself. Your quarks are light, your gluons are weightless, your Higgs field pays a single penny. The other 99 cents are pure energy, converted into mass by the most famous equation ever written. You are Einstein's idea, walking around in a body. Here is a way to feel how much energy hides in you. The energy locked inside the mass of a single human body is enough to power a large city for a very long time. If you could ever release it all at once, the blast would dwarf the largest bomb ever built. You are carrying that much frozen fire inside your bones right now, calm and quiet, doing nothing but keeping you solid. That energy stays locked up on its own, safe, holding your protons and neutrons together, giving you weight and form. The strong force keeps it caged, and it does this every second of your life without you ever noticing. So the picture is nearly complete. You're mostly trapped energy, held by the strongest force in nature, counted as weight by Einstein's rule. Now it is finally time to go inside a proton and witness that trapped energy for ourselves, to watch the storm, because a proton hides a secret. Inside, it is pure chaos. Shrink yourself down small enough to stand inside a single proton, and you would want to run. From the outside, a proton looks like a tiny calm dot, peaceful, simple. Step inside and you find a world gone mad. 3 quarks race around you at speeds so close to the speed of light that they blur into streaks. They never slow down, they never rest. They tear across the proton and slam to a stop and shoot off again over and over, faster than anything in your normal world could ever move. Between them, the gluons flash back and forth in a blinding frenzy. Trillions of them, appearing and vanishing, weaving a web of pure force that yanks the quarks around and flings them back whenever they try to stray. The whole space crackles with energy, like the inside of a lightning bolt that never ends, and it gets stranger. The space between the quarks is alive. It boils. Out of that space, extra quarks pop into being for a flicker of a second, paired with their mirror twins, then wink out again just as fast. They bubble up and disappear constantly like foam on a stormy sea. At any moment, the proton is full of these ghostly extra particles, flashing in and out faster than you could ever catch them. So the calm dot is a lie. A proton is a raging storm sealed inside a shell too small to see. Quarks screaming near light speed, gluons swarming like furious bees, the space itself boiling over with ghost particles, all of it packed into a room 1 trillion times tinier than a speck of dust. And every bit of that chaos carries energy. The racing quarks carry the energy of their motion. The swarming gluons carry the energy of the strong force. The boiling ghost particles carry energy of their own. Add it all together, and you get a colossal amount of energy, trapped in that tiny shell. That trapped energy is the weight. By Einstein's rule, all this frantic motion and roaring force becomes mass. So the storm inside the proton is what tips your scale. When you feel your own body being heavy, you're feeling the weight of 1 trillion tiny storms, one inside every proton and neutron you own. Picture your whole body now as an ocean of these storms rather than flesh and bone. Every atom holds a nucleus. Every nucleus holds these raging protons and neutrons, each one a sealed hurricane of energy, screaming away in silence, giving you your heft. You are a galaxy of tiny storms, wearing the shape of a person. This is why the featherweight quarks barely matter to the total. The quarks are just the seeds of the storm itself. The motion and the force and the boiling energy is where nearly all the weight lives. Take 3 light specks, wear them up to near light speed, wrap them in a roaring field of glue, and the whole bundle weighs 100 times more than the specks alone. Yet one huge question still hangs in the air. If those quarks are flying near light speed, slamming around inside the proton, why do they never break free? Why does the storm never fling one out into the open? Something is trapping them. Something with a grip so total that no quark in all the history of the universe has ever escaped it alone. That prison has a name, and its rules are unlike anything in your world. In all the years scientists have studied quarks, nobody has ever seen a single one alone, not once. Every experiment, every giant machine, every violent smash has failed to pull one lonely quark out into the open. Quarks always come locked in groups, sealed inside protons and neutrons, hidden from the world. This iron rule has a name. Scientists call it confinement, because the quarks are confined, imprisoned, never allowed to walk free. For most things in your world, breaking them apart is easy. Snap a pencil, and you get 2 pieces you can hold. Split a drop of water, and you get 2 smaller drops. Everything you know can be pulled into parts, and each part can stand on its own. Quarks refuse to play by that rule. Try to yank a quark out of a proton, and the strong force fights back harder than you can imagine. The harder you pull, the harder it grips. It will let you stretch it, strain it, pour in enormous energy, and still it will keep hold of its prisoner. Why? The answer lives in how the strong force behaves, and it behaves like nothing else in nature. Every other force you know gets weaker as things move apart. Gravity fades with distance. Magnets lose their grip as you pull them away. Pull 2 magnets apart far enough, and eventually they barely feel each other at all. The strong force does the opposite, and this is the twist that breaks your intuition. The farther you try to drag 2 quarks apart, the stronger the force pulling them back becomes. Up close, quarks can actually drift around fairly freely, almost like they are loose. But the moment one tries to leave, the strong force wakes up and yanks harder and harder the farther it goes. It is a leash that gets tighter the more you stretch it. A prison whose walls push back with more strength the closer you get to escaping. You can run to the edge all you like, and the edge fights you with growing fury the closer you come. So the quarks stay trapped forever, racing around inside their tiny cell, held by a force that only tightens its grip when they try to flee. And all that straining, all that endless effort to hold the prisoners in, pours energy into the proton. That energy, as you now know, becomes weight. The prison itself is heavy, and its heaviness is yours. Confinement is the reason your matter is stable. It is the reason protons hold together for longer than the age of the universe, keeping your atoms whole, keeping you in one piece. If the strong force ever loosened its grip, your quarks would scatter, and every solid thing you know would dissolve into a thin mist. But something truly bizarre happens if you ever do manage to pull hard enough. You would expect that with enough force, the quark finally rips free. That is where the strong force plays its final mind-bending trick. Pour in enough energy to tear a quark loose, and the universe does something that feels almost alive. At the very last moment, it reaches into that stored energy and builds brand new particles out of thin air, just to keep the quark trapped. To see how empty space turns straining energy into fresh matter, we have to watch the rubber band snap. Grab a rubber band and stretch it between your hands. At first, it pulls back gently. Stretch it more, and the pull grows. Stretch it further still, and it fights you hard, straining, storing up energy in every fibre, until finally it snaps. That snap is the band releasing all the energy you poured into it. The bond between 2 quarks works like a rubber band, but a magical one that never seems to run out. As you try to pull 2 quarks apart, the strong force stretches between them like an invisible band, and it pulls back harder the more you stretch. You pour in energy, the band stores it. You pull harder, the band stores even more. The energy trapped in that stretched bond climbs higher and higher. Now think about what all that stored energy is. By Einstein's rule, energy and mass are the same thing. So as you stretch the bond and pump energy into it, that energy is quietly turning into the raw material for mass. You are, without meaning to, building the ingredients for brand new particles. And here comes the trick that feels almost impossible. The moment the stretch bond holds enough energy, it snaps. The snap uses all that stored energy to create two fresh quarks out of nothing. Where you had one bond, you now have two shorter bonds, each capped with a new quark, sealed up tight again. Picture snapping a bar magnet in half, hoping to get a single north pole all by itself. You never do. Each broken piece instantly grows a new south pole, and you end up with two complete magnets. Quarks do the same thing. Try to isolate one, and the universe conjures new quarks from the stored energy to pair it up over and over. You can smash and pull all day, and all you ever make is more sealed bundles, always fresh whole pairs. This is the deepest reason a lone quark can never exist. The very act of pulling one out creates the particles that keep it company. The strong force would rather build whole new matter from pure energy than let a single quark stand alone. Sit with how backwards this is compared to your world. In your life, breaking something gives you smaller pieces. Break a proton bond, and you get bigger, fresh particles instead, born from the energy of the pull. Splitting things apart here creates new stuff, where you expected only scraps. This is Einstein's equation, turned into a machine. Energy pours in, mass pops out. It happens every time particles smash inside those giant machines under the ground, where collisions spray out showers of brand new particles, all built from the energy of the crash. Scientists watch it happen millions of times, matter blooming out of pure energy, exactly as the equation promised. So the quarks inside you are locked in a prison that turns escape energy into fresh matter. And the storm holding them runs on more than quarks and gluons. That boiling space inside the proton is constantly borrowing energy to flash new particles into being, then paying it back a heartbeat later. Those flickering borrowed particles have a ghostly life of their own. They appear from nothing, live for the tiniest sliver of time, and vanish before the universe can catch them. To understand how empty space itself can bubble with these ghosts, we have to look closer at the strangest rule in all of physics. Look at the emptiest place you can imagine. A sealed box with everything sucked out. No air, no light, no dust. Pure nothing. That box is still full. Here is the strangest rule in all of physics. Empty space can never sit perfectly still. It is always trembling, always buzzing, never quiet for even a heartbeat. And out of that trembling, tiny particles are born from nothing at all. They flash into being for the briefest sliver of time, a flicker so short you could never hope to see it, and then they vanish again, paying back what they borrowed. Scientists call them virtual particles. Ghost particles is the better name. They haunt every corner of space, appearing and disappearing constantly, filling the universe with a faint, endless fizz. How can a particle come from nothing? The rule that allows it sounds like a loophole in the laws of reality. For an incredibly short moment, the universe lets you borrow energy from nowhere, so long as you pay it straight back. The shorter the loan, the more you can borrow. A ghost particle takes out one of these tiny loans, uses it to exist for a flash, then repays it and blinks out. The books always balance, but in that flash, the particle was real. Picture the surface of a pot of water just before it boils. Tiny bubbles keep forming and popping, all over the surface. Empty space works the same way. Bubbles of particles fizz up out of nothing, then pop back into nothing everywhere, all the time. The emptiest vacuum is really a boiling sea. Now bring this back to the proton. Inside that tiny shell, the boiling never stops. Ghost quarks and ghost gluons froth up in the storm, live for a flicker, and vanish, over and over, trillions of times. The proton is packed with these fleeting ghosts on top of its 3 real quarks, and every one of those ghosts carries energy while it exists. Even borrowed, even fleeting, that energy is real for the moment it lasts. Add up the constant fizz of countless ghost particles boiling inside the proton, and it piles onto the weight. Part of what you weigh comes from particles that are barely there, flashing in and out faster than time can hold them. Sit with that for a second. Some of your body weight, the number on your scale, comes from things that flash in and out of existence. Ghosts that borrow a moment of life from empty space and pay it back before the universe notices. You're held up, in part, by a shimmer of almost nothing. so the inside of a proton is even fuller than the storm suggested. Real quarks racing near light speed, real gluons swarming, and a boiling froth of ghost particles fizzing through every gap. All of it energy, all of it weight. There is still one more source of your mass hiding in that storm, and it might be the strangest of all. It comes from pure speed. The quarks inside you are moving so fast, so close to the ultimate speed limit of the universe, that their motion alone becomes weight. The faster a thing goes, the heavier it gets, and your quarks never stop running. To see how running in place can make you heavier, we have to break the last rule your everyday world taught you about speed. Speed up a train, and it does not seem to get heavier. Or so your everyday world tells you. In the tiny world inside a proton, that idea breaks completely. There, speed itself has weight. The faster a particle flies, the more it weighs. Push a thing close enough to the speed of light and it grows heavier and heavier, harder and harder to shove, as if the universe were piling invisible mass onto its back. This comes straight from Einstein again. Energy and mass are the same thing. And a moving object carries energy in its motion. The faster it moves, the more motion energy it holds. Since energy is mass, more speed means more mass. A racing particle is heavier than a resting one, purely because it is moving. For a slow train, this effect is so tiny you would never notice. A train crawls compared to light, but the quarks inside your protons are the opposite of slow. They scream around at nearly the full speed of light, the fastest anything can ever go. At those speeds, the weight of motion stops being tiny. It becomes huge. Think of a single quark sitting perfectly still. It would weigh almost nothing, just its little scrap of Higgs mass. Now set it racing near light speed, trapped inside the proton, unable to slow down. Suddenly it weighs far more than it did at rest, because all that motion energy counts as extra mass. The quark did not gain any new parts. It just started moving fast and the speed made it heavy. So a big chunk of your weight is pure motion, movement wound tight, the frantic, endless running of quarks that can never stop, spun so fast that their speed turns into solid heft on your bathroom scale. Here is a way to picture it. Imagine a hummingbird sitting on a branch, weighing almost nothing. Now imagine you could somehow weigh the blur of its beating wings while it hovers. The faster those wings beat, the more that beating would weigh if the world played by proton rules. Your quarks are hummingbird wings beating near the speed of light forever, and their blur is a real part of your body weight. This is why you cannot escape your own mass by holding still. Even when you lie down and relax, even in your deepest sleep, the quarks inside you are racing at their unimaginable speed. They never rest, they never slow. The storm inside every proton roars on whether you move a muscle or not, and its speed keeps you heavy every second of your life. Stack it all up, and the picture of your weight grows clearer and wilder. The gluon field carries energy, the ghost particles carry energy, and the racing quarks carry the energy of their blinding motion. 3 rivers of energy, all pouring into the same tiny shell, all becoming the mass of a single proton, times the trillions of protons that make you. The Higgs field gave your quarks a whisper of rest weight. The storm did everything else. So now a wild question almost asks itself. What would happen if you reached out and switched the Higgs field off, flipped the switch, drained the invisible ocean, and let your quarks lose that whisper of weight for good? You might expect to vanish. The answer is far stranger than disappearing. Imagine a giant switch floating in front of you labelled with 2 words, Higgs field. Right now it is flipped on, and it always has been everywhere in the universe. Reach out and flip it off. What happens to your body? Your first guess might be that you vanish. The famous field that gives mass gone, so surely all your weight disappears with it. That guess is wrong, and the truth reveals everything. The instant the Higgs switch flips off, your quarks lose their rest weight. That whisper of mass they carried, the 1%, blinks away. Your electrons lose their weight too, every scrap of it, since electrons get all of theirs from the Higgs field, so you drop that 1% in a heartbeat. But the other 99% does not care. The strong force is still roaring inside your protons. The gluons still swarm. The quarks, even stripped of any rest weight, still race around near light speed, and their motion still carries energy, and that energy is still mass. Turn off the Higgs field, and your protons stay almost exactly as heavy as before. Almost all your weight simply stays put, held by the storm, so you would barely get lighter at all. Here is the twist that ends you anyway. Those weightless electrons are a disaster. An electron with mass sits neatly around its atom, held in a tidy little cloud. Strip away its mass, and the electron flies off at the speed of light, impossible to hold. Every electron in your body would rocket away and never come back. With no electrons anchored in place, atoms cannot exist. Chemistry falls apart. Every bond that holds your molecules together snaps at once. Your body would dissolve. Every atom would come undone, the electrons gone, the structure collapsed, leaving a spreading cloud of naked nuclei with nothing to bind them. You would stop being a person in an instant, even though most of your raw weight was still floating there in the wreckage. Sit with what this teaches you. The real gift of the Higgs field is structure. It makes you hold together. It builds the tidy atoms, the stable chemistry, the bonds of life. Take it away and you lose your shape, your solidity, your very existence as a living thing, while your weight barely flinches. The headlines had it backwards all along. They said the Higgs gives everything its mass. What it truly gives is form. It builds the scaffolding that lets atoms, molecules, and living bodies exist at all. Your mass was always mostly the strong force. Your shape was always the Higgs. So one switch, flipped off, dissolves you without lightening you. That alone should reshape how you think about the tiny field the world once crowned as the source of all weight. Now grab the other switch. This one is labelled strong force. It is the one holding the real 99% of you together. The storm, the prison, the roaring energy in every proton. Flip that one off, and the result is the opposite kind of nightmare. Where losing the Higgs dissolved you quietly, losing the strong force would tear you apart in the most violent flash the universe can produce. Let us pull that second switch and watch what happens. Your hand is on the second switch now. Strong force, the one holding the real bulk of your weight together. Flip it off. This time you feel it instantly. The strong force was the prison walls around your quarks, the leash that never let them run, the roaring grip inside every proton and neutron. Switch it off, and the prison doors vanish everywhere at once. The quarks, free for the first time ever, scatter in every direction. Every proton and neutron in your body pops open like a balloon. And here is the terrible part. Remember that the mass of your protons was mostly the energy of that trapped storm. The moment the strong force lets go, all that stored energy has nowhere to hide. It floods out. The energy that was quietly pretending to be weight is suddenly released. All of it, everywhere in your body in the same instant. The amount is beyond imagining. Every proton and neutron dumps its hidden energy at once. Your body holds more of these than you could count in 100 lifetimes. The flash would be brighter than the sun, a burst of raw energy unleashed from the 99% that used to be your weight. There would be no body left at all, only light and heat spreading out into space where a person used to stand. So flipping this switch does the opposite of the last one. Kill the Higgs field, and you dissolve quietly while your weight lingers. Kill the strong force, and your weight itself detonates, because your weight was energy the whole time, and energy set free is an explosion. This thought experiment lays the truth bare. Your mass is caged energy. The strong force is the cage. As long as the cage holds, that energy behaves like solid, calm, ordinary weight, sitting patiently on a scale. Break the cage, and it shows its true face. Furious, blazing energy, enough to outshine a star for a moment. You walk around every day carrying that blaze inside you, tamed and silent. Trillions of tiny cages, each holding a scream of energy, each keeping perfectly still. The strong force never tires, never slips, never lets even one of them break loose on its own. That endless discipline is the only reason you are a person and a flash of light. This is why your matter is so stable. The strong force locks the energy in and throws away the key. A proton can sit unbroken for longer than the universe has existed. The cage is that good. Your body trusts it every second without you ever knowing the trust is there. So now you have seen both halves of yourself clearly. 1% of you is the Higgs field, the gift of shape and structure, the reason your atoms hold their form. 99% of you is the strong force, the caged storm of energy that gives you nearly all your weight. 2 forces, 2 switches. One builds your shape, the other builds your heft. Together they make the strange thing you call a body. There is one small piece of you we have brushed past though, a tiny particle that plays by completely different rules. Its weight comes from the Higgs field alone, with no quarks, no storm, and no strong force inside it. It is the electron, and it is the purest Higgs creature in your whole body. Meet the simplest heavy thing in your body, the electron. Electrons are the tiny particles that swarm around the outside of every atom, forming the cloud that gives atoms their size. You have an unthinkable number of them, buzzing through every cell, carrying the electricity that fires your nerves and beats your heart. Every thought you have ever had rode on moving electrons. Here is what makes the electron special. It is a truly fundamental particle. Crack open a proton and you find quarks inside. The electron is a single point, as far down as the universe goes, with no parts at all. It cannot be split, opened, or broken into pieces. There is nothing smaller hiding within it. That simplicity changes everything about its weight. A proton is heavy because of the storm inside it, the quarks and gluons and trapped energy. An electron is just one lonely point drifting through space. It has no storm inside, no strong force gripping it, no gluons to swarm. There is no inside for a storm to live in, so where does an electron get its mass? From one source only. The Higgs field. The electron is the purest example of the Higgs field at work. As it moves through that invisible ocean, the field grabs it and drags on it, and that drag is the electron's entire weight. Every bit of an electron's mass comes from the Higgs field, with nothing else mixed in. No binding energy, no motion of hidden parts, just a single point wading through the ocean, paying its toll and coming out with a small clean mass. If you wanted to see the famous Higgs field doing exactly the job the headlines promised, this is where to look. In the electron, the story the world celebrated is completely true. The Higgs field really does give the electron all of its mass, 100% of it. No hidden storm stealing the credit. So your body has 2 totally different kinds of weight walking around inside it. Your protons and neutrons, heavy from the strong force, barely leaning on the Higgs field at all, and your electrons, weighing whatever the Higgs field alone decides, with no other source in sight. 2 recipes for mass mixed together in every atom you own. This is what makes mass such a rich and strange story. There was never one simple answer. The universe uses more than one trick to make things heavy, and your body runs on both at once. The strong force builds the giants. The Higgs field builds the tiny simple points that circle them. Now you might expect the electron to matter a lot to your weight. It is pure Higgs, a clean and honest source of mass, buzzing through every atom in enormous numbers. Surely all those electrons add up to a real slice of your body. They barely register at all. Line up an electron next to a proton, and the difference is almost comical. The proton towers over it. When it comes to your total weight, the electrons practically disappear, even though there is one for every proton in your body. To see why something so important to life can weigh so laughably little, we have to put an electron and a proton on the same scale, put a single proton on one side of a scale and a single electron on the other. It is the most lopsided contest in nature. The proton outweighs the electron by about 1800 times. 1800. To feel that gap, picture a full-grown hippo sitting on one side of a seesaw and a single grape on the other. That is roughly the proton against the electron. One is a heavyweight giant, the other is a crumb. Your body has one electron for every proton, give or take, all paired up inside your atoms. So you might think the electrons and the protons split your weight somehow. They do not come close. For every pound of protons and neutrons you carry, the electrons add the weight of a whiff. If you could pluck every electron out of your body and weigh them together, the whole pile would come to less than the weight of a single eyelash next to the rest of you. So the electron, the purest Higgs creature you own, the one particle that proves the famous field really works, barely moves your scale at all. It is vital for life, yet nearly weightless in the grand total. This drives home the whole point of our story in one clean stroke. The Higgs field gives the electron all of its mass. The electron then contributes almost nothing to your weight. So even the part of you that is pure Higgs turns out to be a rounding error. The field the world crowned as the maker of mass hands you a feather, then a second feather, and calls it a day. Think back to the penny and the dollar. That single cent of Higgs weight is split between two things. Most of it is the tiny rest mass of your quarks. A sliver of it is your electrons. Add those together and you get your 1%. The strong force, roaring in your protons, pays the other 99 cents. So here is a clean way to hold the truth. Almost all of you is the strong force. A whisper of you is the Higgs field, and that whisper is split between light quarks and even lighter electrons, both so small they barely tip the scale. You are a strong force creature, wearing a thin coat of Higgs on top. It is strange to think the electron matters so little to your weight when it matters so much to your life. Every heartbeat, every nerve signal, every spark of thought depends on electrons moving. They run you. They just do not weigh you. Life leans on the lightest part of you, while your heft comes from the storm you never feel. Now we have every ingredient on the table. The strong force and its storm, the racing quarks and their motion, the swarming gluons, the boiling ghost particles, the whisper of the Higgs field, split between quarks and electrons, every source of your weight, named and measured. So it is time to write the full recipe, the complete list of everything that adds up to the number on your bathroom scale, from the biggest slice to the smallest crumb. When you see it all laid out together, one truth will jump off the page. You are made of far less matter and far more energy than you ever imagined. Let us build the recipe for a human being. If you wrote out a recipe for the weight of a human body, it would shock a chef. Start with the main ingredient, energy from the strong force. This makes up about 99 parts out of 100. It comes in 3 flavors, all stirred together inside your protons and neutrons. The swarming gluon field, thick with the fury of the strongest force in nature. The blinding motion of quarks racing near light speed, and the boiling froth of ghost particles fizzing in and out of the storm. Pour all of that in first. It is nearly the whole dish. Now add a pinch of the Higgs field, just a pinch, 1 par out of 100. Sprinkle in the tiny rest weight of your quarks, which is most of this pinch. Then add an even smaller dash for your electrons so light they barely change the bowl. Stir it into the storm. That is the entire recipe. 99 parts trapped energy, 1 part Higgs. Mix, and you get a person. Read that list again and let the strangeness hit. The thing you think of as your solid physical body is almost entirely energy in disguise. The real, solid, weighable matter, the actual particles with rest mass, makes up a sliver so thin you could round it to nothing. You're a bowl of energy with a garnish of matter on top. Picture it as a giant jar filled with 100 marbles, each marble a piece of your weight. 99 of those marbles are pure energy, trapped by the strong force inside your protons. Only 1 marble is the Higgs field, and even that 1 marble is mostly quark weight with a tiny fleck of electron. Hold the jar up. 99 glowing marbles of caged energy, 1 dull marble of ordinary stuff. That is you. This flips the way people have described themselves for all of history. We say we are made of matter, flesh and bone and blood, solid things you can touch. The deeper truth is that you are made of energy, held in the shape of matter by the strongest force there is. The solid feeling is real, but it rests on a foundation of pure trapped power. So the next time you step on a scale, you can read the number differently. That number mostly measures the energy locked inside you, the trapped power converted into weight by Einstein's rule, and guarded by the strong force in every one of your countless protons. Your weight is a measure of how much energy the universe has trapped inside your body. You are far lighter in true matter than you ever believed, and far heavier in energy than seems possible. Once you accept that most of you is trapped energy, a deeper question opens up. If you're barely made of solid stuff, if you are mostly energy frozen into shape, then what is holding that shape? What keeps the energy from spreading out and fading away? What makes a swirling knot of energy sit still long enough to be a person? The answer touches the deepest idea in all of physics. At the smallest level, the things we call solid particles behave less like tiny balls and more like waves, standing still, humming in place. You are one of those waves, and it is time to see how. Pluck a guitar string and it hums a note. The string vibrates, yet the shape of its wave seems to stand still, quivering in place between the 2 fixed ends. Musicians call this a standing wave. The energy is trapped, bouncing back and forth so fast that it holds a steady humming shape. Deep down, you're made of standing waves. At the smallest level of reality, the particles inside you behave in a way that stretches your everyday sense of solid and empty. A quark, an electron, a speck of matter, acts like a tiny wave humming in place. It is a knot of energy vibrating in the fabric of space, holding a steady shape, the way a plucked string holds its note. What you call a particle is really a little standing wave that refuses to fade. This is the deepest answer to where your weight comes from. Energy, when it gets trapped and forced to vibrate in one small spot, takes on mass. A wave held still, humming in place, weighs something. Set that same energy free to fly away as light, and it weighs nothing. The difference between light and matter, between weightless and heavy, comes down to whether the energy is racing off or trapped and humming. So a proton is a bundle of these trapped humming waves, packed and knotted together, held by the strong force, and you are trillions of those bundles woven into the shape of a body. You are a whole chord, many notes at once, a vast layered hum of trapped energy, all vibrating in place, all adding up to the person reading these words. Think about what that means for the word solid. When you knock on a table, you feel something firm and real. That firmness is standing waves of energy pushing back against the standing waves in your knuckles. Two hums, meeting, refusing to pass through each other. The solid world is a song of trapped energy, played on the smallest strings there are. You are the energy itself, caught in a pattern, playing itself as a person. Pull the stuff out from under the pattern, and there would be nothing left to pull. The pattern is all there is. This is why you can lose and replace nearly every atom in your body over the years and still be you. The atoms come and go. The pattern remains. You are more like a flame than a rock. A flame keeps its shape while the stuff burning through it constantly changes. You're a standing wave that has held its shape for as long as you have been alive, even as the material flows through and out of you. So here you are, a humming knot of trapped energy, shaped like a person, playing a steady note in the fabric of the universe. That is the honest picture of what you weigh and what you are. But this raises the biggest question of all. Where did this trapped energy come from in the first place? Your quarks, your protons, the storm inside them, the caged power that makes up almost all of you. Something had to trap that energy. Something had to build the storm. To find that moment, we have to travel back further than anything, to the first sliver of a second after the universe began. Your weight has a birthday, let us go to it. Rewind the universe all the way to the beginning, past your birth, past the earth forming, past the first stars, all the way to the very first moment, the Big Bang. In that first instant, the universe was unimaginably small, unimaginably hot, and unimaginably dense. Everything that would ever exist, every star, every planet, every atom in your body was packed into a space smaller than a single speck, and it was hotter than anything that has existed since. Trillions of degrees, hot beyond any fire, any furnace, any star. At that heat, nothing you know could survive. Atoms could not form. Protons and neutrons could not hold together. Everything was too hot, too wild, too full of energy for any of them to last. If you had tried to build a proton in that furnace, it would have been ripped apart the instant it formed. The whole universe was pure energy, blazing and churning, with tiny particles flashing in and out of that energy faster than thought. Quarks appeared and vanished. Gluons swarmed everywhere. The building blocks of everything were there, yet they could not lock together. The heat kept smashing them apart as fast as they tried to join. Picture trying to build a snowman inside a raging bonfire. Every time you press the snow together, it melts and scatters before it can hold a shape. That was the early universe for your quarks. Every time they tried to bind into a proton, the ferocious heat tore them loose again. Nothing solid could form. Nothing could last. So in the first slivers of time, matter as you know it simply could not exist. The universe was a screaming ocean of energy and free-flying particles, too hot to settle into anything. The ingredients of your body were all present, floating in that fire, waiting for a chance that had not come yet. Here is the astonishing part. The energy that filled that early universe is the same energy that fills you right now. It never went away. It only changed form. The blazing power of the Big Bang cooled and settled and got trapped over billions of years into the shapes we call matter. The energy in your protons today is a direct descendant of the fire at the start of time. You are made of the Big Bang. The energy screaming in your quarks was screaming in that first furnace. It has been on a journey ever since, cooling, trapping, hiding inside protons, riding through stars and dust, and finally into you. When you feel your own weight, you're feeling a piece of the beginning of everything. But that first furnace was far too hot for any of this to settle. For your weight to exist, the universe needed to cool. It needed to calm down enough for quarks to stop being torn apart, enough for the strong force to finally grab hold and trap the energy for good. That cooling did not take long. In the tiniest fraction of a second, the universe began to change. And in that change, the quarks entered a strange state they would never know again, a brief window when they roamed completely free. For one fleeting moment, before the prison doors slammed shut forever, the quarks were loose. Let us step into that soup. For a flicker at the dawn of time, the universe was a soup. Scientists have a name for it: the quark-gluon plasma. It was the hottest, strangest state of matter that has ever existed, filling the entire young universe. In this soup, quarks and gluons roamed free, swimming through each other, mixing in a boiling sea with no walls and no cages anywhere. This was the one and only time in all of history that quarks got to run loose. Remember the iron rule, that a quark can never be pulled out of a proton alone. In the soup at the start of time, that rule had not yet clamped down. The universe was so hot and so dense that quarks could not be caught and held. They flew everywhere, free particles in a free ocean, tasting a liberty they would lose forever a heartbeat later. Try to picture this soup, hotter than the center of any star, denser than anything you could touch. A churning sea where the building blocks of all future matter swirled together with nothing to bind them. Pure ingredients waiting to be cooked into protons. Every quark that would ever sit inside your body was somewhere in that soup, roaming free, part of a sea that filled all of space. Scientists have actually made a tiny drop of this soup on purpose. In the giant machines under the ground, they smash heavy particles together so violently that for the briefest instant they recreate the heat of the early universe. In that flash, a speck of quark-gluon plasma appears, the same state that filled the cosmos at the beginning. It vanishes almost instantly, but they have seen it. They have made a crumb of the dawn of time in a laboratory. What they found is that this soup behaves like a perfect liquid, flowing more smoothly than any liquid on Earth, with almost no friction at all. The first stuff in the universe was the smoothest fluid there has ever been. A river with no drag, made of the free building blocks of everything. But a universe cannot stay that hot. From the first instant it was expanding, stretching, spreading out in every direction. And as it spread, it cooled. Like a hot pan pulled off the stove, the searing soup began to lose its heat. Slowly at first, then fast, the temperature dropped, and cooling changed everything. As the soup cooled, the wild energy that kept the quarks apart began to fade. The quarks slowed. They started to feel the pull of the strong force reaching out to grab them. The window of freedom was closing. The cages were about to form. This is the turning point of the whole story of your weight. In the soup, the quarks were free and the strong force could not hold them. As the heat drained away, that was about to flip. The strong force was waking up, stretching out its short, powerful arms, ready to seize the quarks and lock them away for good. The moment it did, something was created that had never existed before. Protons, neutrons, the heavy giants that would one day become you. And with them, in that same instant, came the 99% of your weight. Your mass was about to be forged. Let us watch it happen. About 100,000th of a second after the universe began, the great trapping happened. The soup had cooled just enough. The quarks had slowed just enough, and in that instant, all across the young universe at once, the strong force reached out and slammed its cages shut. Quarks that had roamed free were suddenly grabbed, 3 at a time, and locked together. Protons and neutrons blinked into existence everywhere, in unimaginable numbers, in the same tiny fraction of a second. Scientists call this moment hadronization, a big word for a simple, staggering event. It is the moment ordinary matter was born. Before it, free quarks in a soup. After it, protons and neutrons, the heavy building blocks that fill every atom in the universe today, including every atom in you. And here is the part that ties the whole story together. The instant those quarks got trapped, the strong force began pouring energy into holding them. The storm switched on, the gluon field roared to life. The quarks, caged now, raced inside their tiny prisons near the speed of light. All that trapped energy, by Einstein's rule, became weight. In that single instant, the 99% of your mass was created. Sit with the size of this. Before hadronization, the ingredients of your body had almost no mass to speak of, just the feather-like quarks. After hadronization, those same quarks were wrapped in a storm of trapped energy that weighed 100 times more. The universe simply trapped the energy that was already there, adding no new stuff at all, and that trapping turned the energy into weight. Almost all the mass of every solid thing that would ever exist was forged in that heartbeat. Your weight has a birthday, and this is it. 100,000th of a second after the beginning of everything. That is when the energy destined to become you got locked into the shape of protons and neutrons. It has been carried inside them ever since through billions of years, waiting to become a person. Think of what those protons have been through since that day. They floated in the young universe. They gathered into clouds of gas. They fell together to build the first stars. They were blasted out when those stars died, scattered across space, swept into new clouds, and finally gathered into the Earth, into the food you eat, into the cells of your body. The same protons, forged in that first instant, carrying the same trapped energy, all the way to you. You are ancient. The weight you carry is nearly as old as time itself. The energy in your protons was trapped before there were stars, before there were galaxies, before there was anything but a cooling soup, and it has never once been released. The cages have held for the entire life of the universe. So the story of your weight is really the story of the cosmos learning to trap energy. First the fire, then the soup, then the great slamming of the cages, freezing energy into mass in the blink of an eye at the start of time. But the universe had another trick still to come, because once matter existed, it began to gather and burn, and in the hearts of stars that trapped energy would start to break loose again, in a way that lights up the whole night sky. Let us go inside a star. Deep in the heart of a star, matter does something it can do nowhere else. It turns weight back into light. A star is a giant ball of gas, mostly the lightest stuff in the universe, squeezed by its own enormous gravity. At the very center, the crush is so intense, and the heat so extreme, that the tiny cores of atoms are forced to slam together and stick. Scientists call this fusion. Small cores merge into bigger ones over and over, powering the star. Here is the magic hidden in that merging. When the small cores fuse into a bigger one, the new core weighs a tiny bit less than the pieces that made it. Some mass goes missing. That missing mass turns into energy, exactly as Einstein promised, and comes blasting out as heat and light. This is the whole story of our world running in reverse. Everywhere else, energy got trapped and turned into weight. Inside a star, weight gets released and turned back into energy. The star is unlocking a few of the cages, letting a sliver of trapped mass escape as pure light. The amount of mass that goes missing in each merge is tiny, but stars do this an unthinkable number of times every second, in a core larger than many planets. Add up all those tiny scraps of vanished mass and the energy pouring out is staggering. It is enough to light up a whole solar system and keep it warm across the empty dark. That light on your skin from the sun is trapped mass, set free. Every sunbeam that has ever warmed your face was once weight, sitting inside the sun, until fusion turned it into light and flung it across space to reach you. The warmth of a summer day is the sun quietly turning a piece of itself into energy and sending it your way. Think about how strange this is next to everything you have learned. Your weight is energy that got trapped and frozen into matter. Sunlight is matter that got untrapped and freed back into energy. The two are the same process, running in opposite directions. The universe traps energy to make mass, and stars release mass to make energy, both obeying the same short equation. This is why stars shine for billions of years. They are slowly cashing in their own mass, converting weight into light, a little at a time. A star is a machine for turning matter back into the energy it came from, glowing the whole while it works, and it means the stars are slowly getting lighter. Every second a star shines, it weighs a little less than the second before, because it has thrown away some of its mass as light. The brighter it burns, the faster it sheds its own weight. A star pays for its light with pieces of itself. Our own sun does this right now, every second, without pause. It has been shining for billions of years, and it will shine for billions more, steadily turning its mass into the light that grows our food and warms our world. So how much of itself does the sun throw away to keep shining? The number is so large it almost breaks the mind. Every single second, the sun destroys a piece of itself heavier than a mountain and turns it into light. Let us weigh what the sun loses. Every second, the sun turns about 4 million tons of itself into pure light. 4 million tons, gone, every second. To picture that, imagine a herd of elephants, hundreds of thousands of them, vanishing in a flash and turning entirely into sunshine, and then it happening again the very next second, and the next, without ever stopping. That is the weight the sun sheds every tick of the clock. It has been doing it for billions of years. In the time it takes you to read this sentence, the sun has destroyed millions of tons of its own body and flung the energy out into space. A tiny fraction of that energy lands on Earth, and it is enough to grow every plant, feed every animal, and warm the whole planet. Here is what makes the number so wild. Even losing 4 million tons a second, the sun is so enormous that it barely notices. It is like a mountain losing a single grain of sand each second. The sun is so massive that it can pour out this river of energy for billions of years and still have plenty left. Its sheer size is why it can afford to be so generous with its own weight. Now, connect this back to you. That 4 million tons the sun loses each second is mass turning into energy, the same kind of trapped energy from the beginning of time finally breaking loose. The sun is running Einstein's equation at a colossal scale, cashing in its mass for light. And that cashing in is what makes life on Earth possible. Take away the sun turning weight into energy, and there is no warmth, no plants, no food, no you. So you owe your life to mass being destroyed. The energy that grew the food in your body came from the sun killing off pieces of itself, 4 million tons at a time. In a strange way, the sun spends its own weight so that you can have yours. Every meal you have ever eaten traces back to sunlight, and every sunbeam traces back to the sun turning matter into energy. Step back and see the full circle now. At the start of time, energy was trapped and frozen into the mass of protons. Those protons gathered into stars, and now the stars are slowly untrapping that energy, turning mass back into light, feeding new life like yours across the dark. Trapped, then freed. Frozen into weight, then melted back into energy. The universe breathing in, then breathing out. You sit right in the middle of that circle. The trapped energy in your protons was frozen at the beginning. The energy that keeps you alive comes from stars unfreezing their own mass. You are both halves of the story at once, a knot of trapped energy, fed by the release of trapped energy somewhere else. There is one last question hiding in all this. The sun turns only a sliver of its mass into energy, a tiny fraction, using fusion. Your protons hold their trapped energy tight, almost never letting go. So is there any way to release all of it at once? To take a body or any lump of matter and turn every last bit of its mass back into pure energy? There is exactly one way, and it requires the strangest substance in the universe, a mirror version of matter itself. Let us meet antimatter. Somewhere out in the universe, for every kind of particle you are made of, there is a mirror twin, an opposite. Scientists call it antimatter. An antimatter particle looks almost exactly like its normal partner, with one thing flipped, like a reflection in a mirror. For the electron there is an anti-electron. For the quark, an anti-quark. They are real. Scientists make tiny amounts of antimatter in their machines, carefully a few particles at a time. Here is what makes antimatter the most dangerous substance imaginable. When a particle of matter touches its antimatter twin, both vanish in a flash and every bit of their mass turns instantly into pure energy. All of it. 100%. Only a burst of light and power remains. This is the one process in the universe that cashes out mass completely. Fusion in a star frees a sliver, a tiny fraction of the mass. When matter meets antimatter, the whole weight of both releases at once, every trapped scrap of energy, in a single instant. It is the universe collecting on the full debt. All the energy that was frozen into that matter since the beginning of time, paid back at once. Imagine taking a small paperclip and its antimatter twin and letting them touch. The energy released would rival a powerful bomb from two objects you could barely feel in your hand. That is how much energy is trapped inside ordinary matter, waiting, hidden, disguised as harmless weight. Antimatter is the key that unlocks every cage at once. Now think about your own body in this light. All that trapped energy we have talked about, the 99% locked in your protons, the storm, the cage power older than the stars, it is all still in there, held tight. Fusion could never touch most of it. Only meeting an equal amount of antimatter could release it all. If your body ever met an antibody of the same size, the two of you would turn entirely into energy, a flash brighter than anything a human has ever built. The energy hiding in a single human body, released all at once this way, would be beyond enormous, enough to dwarf the largest bombs ever made. You carry that much frozen power inside you every day, calm and quiet, disguised as flesh and bone. The strong force keeps it locked. Only its mirror opposite could ever set it free. This is the final proof of what you truly are. Your weight is a vast store of energy, held in check by the strong force, so complete that unleashing it would take the rarest substance in the universe and would light up the sky. You are a battery charged at the dawn of time, and the charge has never once leaked. Lucky for you, antimatter is almost nowhere to be found. The universe, for reasons scientists still puzzle over, is made almost entirely of ordinary matter. Your trapped energy is safe, the cages will hold, you get to walk around as a person, carrying a hidden blaze that will almost certainly never be released. So we have travelled from your bathroom scale all the way to the mirror edge of reality. Now it is time to come home, back to the solid ground under your feet, the floor you trust to hold you up, and one last shock about how solid it really is. Stamp your foot. You are about to learn what is truly there. Stamp your foot on the floor. It feels rock solid. It stops your foot cold and holds up your entire weight without budging. That floor is almost entirely empty space. You learned this about your own body earlier. It is true of everything. The floor, the walls, the chair, the ground outside, all of it is mostly nothing, just like you. Every object in your world is a vast emptiness with a scattering of tiny dense specks, the nuclei, floating far apart inside it. If the floor is basically empty, and your foot is basically empty, then why does one hold up the other? Why do you not simply fall straight through? The answer is a force, reaching out where the emptiness leaves off. The outside of every atom is a cloud of electrons. When your foot presses down, the electrons in your skin get close to the electrons in the floor, and electrons push each other away, hard, with the same force that runs magnets and electricity. They repel. That pushes what you feel as solid. So when you touch the floor, your atoms never actually meet the floor's atoms. They get close, and their electron clouds shove against each other, and that shove holds you up. The solid, firm feeling of standing on the ground is really the feeling of countless tiny electric pushes, holding two clouds of emptiness apart. You have never truly touched anything in your life. The floor, this chair, another person's hand, all of them stay a hair out of reach. Every time you think you're touching something, you're feeling the push of electrons refusing to let two empty spaces overlap. A hair's breadth of nothing always sits between you and the world, bridged only by that force. The most solid handshake is two clouds of energy, hovering, never quite meeting. Put it all together, and the everyday world turns inside out. The ground you trust is mostly empty. The specks inside it are mostly trapped energy. And the solid feeling of standing on it comes from force alone, electric pushes across tiny gaps. You are a cloud of energy, standing on a cloud of energy, held apart by invisible pushes, weighing a number that is mostly caged power from the start of time. Everything about the solid world runs deeper than it seems. The firmness is real, in the sense that it holds you up and keeps you from falling. Yet underneath, it is built from emptiness, energy and force, with almost none of the solid stuff your senses insist is there. This is the final layer peeled back. Your weight is trapped energy. Your matter is standing waves. Your solidity is electric push across tiny gaps. Every comforting, ordinary thing about your physical world rests on ideas far stranger than anyone would guess from the outside. And now you are ready for the whole picture, seen at once. Everything we have travelled through, from the scale in your bathroom to the birth of mass at the start of time, folds into a single, simple, staggering truth about what you are. You're barely made of matter. You're a knot of ancient energy, tied by the strongest force in nature, humming in place, held together and held up by forces you never feel. Let us stand back and look at the whole of it. So here is the whole truth gathered into one picture. You stepped on a scale at the start of all this, believing it measured how much stuff you are made of. It measured a pull instead. Under that pull sat your mass, and under your mass sat a secret the whole world got wrong. Almost none of your weight is stuff. The Higgs field, the thing headlines crowned as the maker of mass, pays for a single penny of your dollar. It gives your quarks a whisper of weight, and your electrons their tiny share, and then its work is done. 1%. A rounding error dressed up as the answer. The other 99% is energy. Trapped, roaring, ancient energy, frozen into the shape of protons and neutrons inside every atom you own. The strong force, the mightiest force in nature, holds that energy in tiny cages, and by Einstein's rule, caged energy weighs exactly like solid matter. So the number on your scale is mostly a measure of how much energy the universe has locked inside you. And that energy is old. It was born in the first fire, cooled in the quark soup, and trapped in a single heartbeat 100,000th of a second after time began. It has ridden inside your protons ever since, through the birth and death of stars, through the making of the earth, into your food, into your cells, into the living person reading these words. The weight you carry is nearly as old as the universe, and it has never once been set free. You are a knot of energy that the universe tied at the dawn of time and simply never got around to undoing. Think about what that makes you. A pattern, a standing wave, humming in place, holding its shape while atoms flow through you and out of you your whole life long. A bonfire the cosmos froze into the form of a person, still roaring inside every proton, still screaming near the speed of the light, and yet calm enough to sit still and wonder about itself. That is the strangest part of all. This trapped energy, this ancient storm somehow woke up. It became you, a bundle of frozen fire that can look at a scale, ask where its weight comes from, and follow the answer all the way back to the beginning of everything. The universe took a piece of its first fire, hid it inside you, and let it become something that could understand its own hidden blaze. So the next time you step on a scale, you will read the number differently. It counts starlight from before there were stars, energy from the first instant, held in the strongest grip in nature, riding around in the shape of you. You're barely matter, you're mostly energy. You're almost entirely empty space, held open by forces you will never feel, carrying a blaze from the start of time that could light up the sky if it ever broke loose, and it never will. The cages will hold quietly for as long as you live, keeping the fire tame, keeping the shape whole, keeping you here. You're a piece of the Big Bang, still warm, walking around, wondering, and now, at last, you know exactly what you weigh.